Hello everyone and welcome back to MV Tutors. I'm Tsolo and I'll be looking at the chemistry November exam from 2023. And without wasting any time, let's get right to it. I heard a lot of complaints about this paper. I think so far the maths paper went well, both papers. Yes, tricky questions here and there. Physics also not so bad, but chemistry. So I'm still to find out where the tricky parts were. So let's just do question 1. Please don't forget to like our videos and also subscribe to our channel. And also tell a friend about our channel when you are practicing, when you are studying, and keeping up with the work that is prepared for you for 2024. So let's get right to it. So multiple choice questions. 1.1, which one of the following represents a straight chained saturated hydrocarbon? So they put there in capital letters saturated, meaning that we're looking at alkanes, and the formula for an alkane is CnH 2n plus 2, right? And here I see we have C5 and we have C6, so we need to choose which one is correct. Let's start with C5. So with H, I'm going to get 10 plus 2, so that's 12. And with C6, I'm expecting 12 plus 2, which is 14. So which here shows the correct answer. So for C5, we have H8, no. That's more of your alkyne. C5, H10, that's your alkene. That's not going to work. Option C, that's also an alkene. Option D, that is your alkane. All right, so D is the correct answer. And then 1.2, which one of the following is a secondary alcohol? All right, so a secondary alcohol, remember, where we have the OH group, the carbon is attached to two other carbons. So we're looking for something like that, okay? That's a secondary alcohol. So if you have a look at the first option, let me just draw all of them out. Let's just do the structural formula for each. So the first carbon is attached to three other carbons because you have CH3, 3 times. So 1, 2, 3, you have a carbon there with its hydrogens. I'm not going to put them in. And now you also have an OH group. Okay, so in this case, we're looking at a tertiary alcohol because the carbon where the OH group is attached to other 3 carbons. So that's not it. If we have a look at B, so the first carbon has its 3 hydrogens. Then you have 2 more carbons, which both have 2 hydrogens. No, actually it's 3 carbons. And then you have your OH group. Okay, so this one is a primary alcohol because the carbon attached to the OH group is attached to only other 1 carbon. Okay, so we're not there yet. We're not there yet. Secondary. Option C, we have a carbon with 3 hydrogens and we have 2 more carbons, each with 2 hydrogens. And then we have another carbon with the OH group. No, this one doesn't look correct because now we need to have 4 bonds around carbon. So actually that's a double bond to oxygen and your H. So this is definitely not an alcohol. Okay, we're looking here at an aldehyde. So D, then it has to be D. Okay, so we have 1, 2, 3 hydrogens, a carbon with 2 hydrogens, then we have a carbon with 1 hydrogen and an OH group, okay, and then 3 other carbons. So you see here this carbon is attached to 2 other carbons, so this is the correct answer. Okay, D is the correct answer. Alright, so now we're going to look at 1.3. So it says, which one of the following is a hydrolysis reaction? Remember, a hydrolysis reaction is a substitution reaction where we have a haloalkane plus a base, okay, a base like your potassium hydroxide or whatever, sodium hydroxide, and then you get an alcohol plus salt. All right, so if they tell us that which one of the following, or ask which one of the following is a hydrolysis reaction, I'm looking for a haloalkane, and I'm looking for a base as well, and I'm looking for alcohol and salt as a product. So if I look at A, yes, I do have a haloalkane. Water is a base. It can be a base or an acid, but in this case it is a base. And then we have an alcohol as well as a salt, so A is an option. B, I have an alcohol there, so no. It's more like a reverse reaction, so no. So B cannot be it. If I look at C, there I see hydration, so no, that's an addition reaction. D, hydrogenation, so no, addition reactions. So A is my only option basically, and I'll go with that. Okay, and then when it comes to 1.4, so it says we have hydrochloric acid that reacts with excess zinc. All right, so whenever they put something in bold, that's really something that you should really be aware of. All right, so in this case, if they say we have excess zinc, it means that the zinc is not used up, all right, when the reaction is finished. Okay, so in this case, the hydrochloric acid then becomes the limiting reagent, okay, or reactant. So yeah, so zinc will not be done, but hydrochloric acid will finish first. Okay, so now it says different reaction conditions are shown in the diagrams below. The mass of zinc used is the same in both test tubes. Okay, that helps. So for test tube X, we have a volume of 100 cubic centimeters and a concentration of 0.1, and the zinc is powder. Test tube Y, we have 200 cubic centimeters as the volume, the same concentration as test tube X, and we have the same amount or the same mass as zinc, but this time it's in lumps. All right, so now the question is, how will the initial rate of reaction and final volume of hydrogen gas produced in test tube Y compare with that in test tube X? So the initial rate of reaction in Y, well, Y has zinc lumps, okay, whereas X has zinc powder. So the rate of reaction will be lower for Y than it is for X. Okay, so now we are left with options B and C at our disposal. Now the final volume of hydrogen gas in Y. All right, so we see here that we have a lot, a bigger volume of hydrochloric acid in test tube Y compared to that in test tube X. Okay, so if we were to calculate the number of moles for test tube Y, remember the equation, we have concentration is equal to number of moles over volume. Therefore, number of moles is equal to concentration times volume. So when you multiply, when you get the number of moles in test tube Y, they're going to be more, okay, than that of test tube X. So therefore, you are expecting then to produce, since zinc is in excess, you'll have more of your hydrochloric acid, more of your hydrogen atoms, so more of the hydrogen gas will be produced in test tube Y as opposed to X. Okay, so if we have then, more will be for option B. All right, so B actually then takes the prize here. Okay, and then now moving right along to question 1.5. So it says the diagram below represents a mixture of nitrogen dioxide as well as dinitrogen tetraoxide molecules at equilibrium in a 1 cubic decimeter container at temperature T. Okay, so basically then for your nitrogen dioxide, you're looking at a concentration of what? Number of moles over volume. So nitrogen dioxide is the one in black. We have 4, 8, 12. All right, so we have 12 cubic decimeter moles per cubic decimeters. That's not how you write it. you say per cubic decimeters. Okay, and then when it comes to dinitrogen tetraoxide, all right, so there the concentration would be, so we have 246, okay, 6 mole per cubic decimeters. All right, that's just putting it out there. We'll see going forward what it is that they want from us. Now they're saying the balanced equation for the reaction is that. So we have 2 moles of your nitrogen dioxide on the reactant side. On the product side, you have 1 mole there. Okay, so yeah, that makes sense. You have double that of nitrogen dioxide as opposed to dinitrogen tetraoxide. So now it says which one of the following is true for the value of the equilibrium constant Kc for the reaction at T degrees Celsius. All right, so remember our Kc formula. It is the concentration of the products divided by the concentration of the reactants. Okay, so if, let's just say hypothetically, we were to calculate it, so the concentration of your product, which is N2O4, that would be 6, and the number of moles there, okay, that's just 1, so it's to the power 1. And then your reactants, you have 12, and then you have 2 moles of nitrogen dioxide, right? So to the power 2. So we can see then our Kc value ultimately is less than 1. Okay, so you have like what, 6 over let's just see, 6 over 144. Okay, so it's definitely less than 1. All right, so if you look at the options, Kc is 24, no. Kc is bigger than 1, no. Kc is equal to 1, no. Kc less than 1, yes. Is it also bigger than 0? Definitely, it is not a negative. So in this case, D would be the correct answer. And then 1.6, let's just raise this up. So now it says, a reaction is at equilibrium in a closed container according to the balanced or the following balanced equation. Okay, so yeah, whatever happened. Maybe this is where your reactants and this were your products. So this is where we were. Okay, and then now the volume of the container is now increased. So if you increase the volume, you decrease the pressure. So what are we looking for? We're looking for the most number of moles. Okay, but gas. Okay, gas. So we see we have copper oxide, which is a solid, and copper 1 oxide, which is a solid, and there we have oxygen gas. So the products are favored. Okay, so O2 there. Yeah. And then now it says the volume of the container is now increased. We've dealt with that, while the temperature remains constant. Okay, so if temperature is constant, what does that tell us? It tells us, okay, I see the table here. It means that the equilibrium constant will remain the same. Okay, so temperature that is constant, it means Kc stays the same. All right, now which one of the following combinations is correct for the new equilibrium? All right, so we know that the temperature, the Kc remains the same, right? So we have options B, C, and D. And so yeah, volume had an effect, something happened, but a new equilibrium was reached. So when we're looking at concentration of oxygen, in this case, I would say that it remained the same, because once you reached equilibrium, you're not expecting any increase or decrease. It should remain the same. Okay, so yeah, column 3. Now I've shifted to column 1, and I'll end with column 2. So column 1, what do we have? We have B and C. Okay, so D is out. We're left with B and C. Now looking at column 2, yeah, well, technically it's, yeah, never mind. Anyway, if you take equilibrium constant as column 3, concentration of oxygen as column 1, then number of moles of oxygen is column 2. The A, B, C, D column we'll just ignore. So now our column 2, number of moles of oxygen, we have B and C as our options. Will it decrease or will it increase? Because here the number of moles that we had were most for oxygen due to the increase in volume, I would say that the number of moles, increases. Okay, so I would go with C for this case. I don't think they would decrease. I don't know, but yeah, I really do think it's C. You can comment below if you beg to differ. Okay, and we can discuss. 1.7. So it says nitric acid and ethanoic acid of equal volumes and concentrations were compared. All right, equal volume, equal concentration. So what, the number of moles are the same for both? Okay, good to note. Yeah, remember C is N over V. Number of moles, concentration times volume. So equal volumes, equal concentration. So both nitric acid and ethanoic acid have the same number of moles. Now consider the following statements regarding these solutions. Okay, let's see. 1, they have different pH values. Most definitely. Nitric acid is a strong acid. All right, I hope you know that. It is a monoprotic acid. Also, ethanoic acid is monoprotic, but it is a weak acid. So definitely they will have different pH values. The one for the stronger acid, nitric acid, it will have an even lower pH value than ethanoic acid. So I agree. That is correct. Both have the same electrical conductivity. No, because nitric acid is a strong acid which will ionize almost completely, if not completely. It will not have the same electrical conductivity as the weak acid. So that is false. And then the third one, all right, it says both solutions require the same number of moles of potassium hydroxide for complete neutralization. Okay. Yeah. So for neutralization, I mean, I would say no. I would say nitric acid will work well because it's a strong acid. You have a strong base, so they will both neutralize each other. But because they say complete neutralization, time here is not really a factor. So this is a tricky one because both nitric acid and ethanoic acid are monoprotic acids, meaning they each have one hydrogen atom that they can, play with. So I would say both solutions, they do require the same number of moles. And remember, they both have the same number of moles there, all right, as we've shown here before. So I would say both solutions require the same number of moles for complete neutralization. The rate at which the neutralization will occur, that will be different, definitely, but I would say number 3 is true. Conflicting one, but I would say it's true. Okay, so now having done that, which of the above statements are then true? 1 only, no. 1 and 2, no. 1 and 3 only, I would say C. And 2 and 3, no. So we're good. 1.7 is C. Okay, and then 1.8. Let's take it a bit up. All right, so 1.8 says the apparatus in the diagram below is used for the titration between hydrochloric acid and potassium hydroxide. Okay, so this titration mixture in there should be the potassium hydroxide, and then you are putting in hydrochloric acid. Okay, probably in a controlled manner. Now it says in a titration, the learner accidentally exceeds the endpoint. Okay, meaning they poured more hydrochloric acid than required. So which one of the following will be true for the titration mixture? So if it was poured at the right amounts, hydrochloric acid as well as potassium hydroxide would neutralize one another. Okay, your pH would be around 7. the concentration of your acid will be equal to the concentration of your base. But now we have more of the acid. So the concentration of your acid will be more than that of the base, and the pH, because it will be more acidic, will be less than 7. And if you look at all the options that are given to you there, pH less than 7 is for A and B, but your H plus ions, the concentration of it is more than the concentration of your OH minus, your hydroxyl ions. Okay, so A in this case then would be the correct answer. Okay, so 1.9, we are almost there with question 1, and so far not so bad. So it says the following hypothetical standard reduction potentials relate to a galvanic cell. Okay, galvanic cell, remember, that's your voltaic cell, where at the end of the day the EMF should be positive. If it's negative, then it means you're dealing with an electrolytic cell. Okay, so we have the first one, X2 plus, and then yeah, we see that the EMF is positive 0.10. In this case, I would say that would be the cathode. Okay, so the X2 plus, blah blah blah, I would say that's part of the cathode, where reduction occurs, red cat. And then the Y plus, if you have a negative there, I would say that's the anode, okay, where oxidation occurs, and ox. All right, so now it says consider the following statements for this galvanic cell. So the EMF of the cell is 0.2 volts under standard conditions. I would agree, because remember EMF, okay, EMF is basically that of the cathode minus the anode. Okay, and the cathode, it's 0.1 minus 0.1, so that's 0.2. So I agree with statement number 1. And then statement number 2, it says electrode Y is the anode. Yes, we did say that. Okay, and statement number 3, X is oxidized. No, remember X, we said it is the cathode, so therefore it is reduced. So yeah, that is not correct. So now, which of the above statements are true for the galvanic cell? 1 only? No. So basically looking for 1 and 2. So that is B, right? Because 1 and 3 is incorrect, 2 and 3 is incorrect. Okay, and the last question, 1.10. So which one of the half reactions below will be the main reaction at the anode during the electrolysis of concentrated copper chloride? Okay, so the main reaction, that main is in caps, at the anode. Ooh, okay, let's make notes. So there are 2 reactions. Okay, remember this is concentrated, so there's water present. Okay, so there's I'm looking at the options here. A, okay, let's just do it this way. We have an electrolytic cell. Okay, this is your anode, this is your cathode. The solution is in there. So the solution, there's water. Okay, there's also copper chloride, but it would have dissociated. Okay, it would have, yeah, spread around basically. So you have all those reactions going on. You have your water, you have your H2, you have your oxygen, you have your copper 2 plus, you have your chloride ions, and the works. Okay, maybe I should have put that as O2. All right, so you have all of that in the mix, and we have our anode. Basically our electrons are going, okay, positive, negative. All right, anode, that's where oxidation occurs, and cathode, that's where the reduction occurs. So which one of the following half reactions below will be the main reaction at the anode during the electrolysis of concentrated copper chloride? So we want to get copper out of this. So what is being reduced then? So A has to do with reduction. Okay, so that's basically at the cathode. I'm just going to say red cat. B, no, we're not really trying to form hydroxyl ions. So B, we're not even going to consider that. C, yeah, we have water and yeah, then we get oxygen, hydrogen. That is a possibility because they said the main reaction. So C and D are both reactions that could occur. But which one is the main reaction? Is it C or is it D? Okay. Now the other capitalized word, it's concentrated. So concentrated will be what helps us to decide between C and D, which one is the correct one. Okay. So because it's concentrated, D will be the correct answer. Okay. It'll be a chlorine gas that will escape there. Okay, instead of your oxygen gas. So in this case, D would be the correct answer. So when you have these kinds of questions, you can get more than one reaction, but make sure you know which one is the main reaction, okay? And in this case, which one between C and D is more likely to be oxidized? Yeah, if you know D is more oxidized, then yeah, we're gonna go with D in this case, okay? And that sums up question 1. Remember what I said, how long should it take us? Well, 180 minutes, 150 marks. It should take us 1.2 minutes per mark. If we multiply that by 20, it's okay to have scientific notation, 24 minutes basically. So let's see, where are we? 27. Okay, we exceeded the time. So in other questions, you make sure that you spend less time. Okay. Question 2. So we are busy with organic chemistry. And the letters A to H in the table below represent 8 organic compounds. All right, so you know me, I like doing this question differently. This time it's not worth a lot of marks. It's just 16 marks. So I'm going to go through A to H and see if I can simplify the information for myself so that this question goes by quickly. So this is 16 marks. So how much time should I be spending on it? 19 minutes. 19 minutes. Let's see if we can do it in 19 minutes. So A, we have heptanoic acid. All right. So hept, that means 7. So we have 1, 2, 3, 4, 5, 6, 7. Okay. And the hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, and we have 2 oxygens. So heptanoic acid, that's a carboxylic acid. Okay, now let's go to B. So we have that structure over there, and we have kuch, not ku. So we're dealing with an ester. Okay, so this is a carboxylic acid. This is an ester. Now what is that ester made of? So I have CH3, 1, 2, 3. And then I have 2 carbons. No, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6. Alright, then I have another C, double bond to O. So this point here, that would be our carboxylic portion of the ester. And this portion over here, that would be the alcohol. Okay. Alright, so what would we call this ester? Well, we have 1, 2, 3, 4, 5. So we have pentanoic acid. In the ester, it's a pentyl. And then 1 pentyl methanoate. Okay, it's an ester. How many carbons? We have 6 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And how many oxygens? We have 2 of them. Alrighty, now we go over to C. We have 4 ethyl, 3,3 difluorohexane. So hex, we have 6 carbons. 3, 4, 5, 6. Okay, if I start counting from the left, when it comes to the third, we have fluorine. Wait, is fluorine just, is it FL or just F? Let me not put my own things. Fluorine is just F. Where am I getting this L? So we have fluorine over there. Question 2. Yeah. So we have 3,3 difluorohexane, and then on the 4th carbon we have an ethyl. So not a methyl, but an ethyl. All right, how many carbons? You have 1, 2, 3, 4, 5, 6, 7, 8. Hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And we have 2 fluorines. All right, so we got that. And then D, hexanoic acid. Okay, that's just straightforward. 1, 2, 3, 4, 5, 6. All right, we have 6 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens and 2 oxygens. Then we go to E. What do we have there? Okay, so they've drawn the structure for us. I'm just gonna, yeah, you see the student that I got this paper from already made some marks. But yes, the way they numbered is indeed correct. So I'm gonna start numbering, actually 1, the first carbon, I'm gonna take it up there, okay? So I'm gonna start with the CH2 at the top and then double bond. So C, double bond, I'm gonna start with that. And then we have another C, and then a C and an H, and a CH3. And then the last one we have CH. I think they made a mistake. I think they were supposed to put a CH3. Unless, of course, if they wanted to put a triple bond, which I doubt. So I think that is CH3. So let's just check. The first carbon, CH2. The second carbon has a methyl group to it. All right. So yeah, the second carbon has a methyl group. The third carbon also has a methyl group, and the last carbon. Okay, so now that we've drawn the structure in a way that is easily done, we can see that we have an alkene. Okay, what kind of alkene can we say it is? So on the second carbon, okay, this is bute. First of all, the longest chain is 4 carbons, so we can say this is bute 1 ene. And just to make sure that I drew it correctly, actually this methyl group that I put there, let's just see, first carbon, second carbon. Okay, no, why did I erase that? Second carbon, third carbon. So we have a 2,3. Yeah, I shouldn't be doubting myself. 2,3, and it's a dimethyl bute 1 ene. Okay, so E, I think we're sorted there. How many carbons? I have 1, 2, 3, 4, 5, 6. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, that's just it. Okay, yes, it is, because it's a it is a alkene, so CnH2n. Now F, what do we have? All right, it's already drawn for us. There's no need for us to actually redraw it. But how can we name it? So I can see on the second carbon, I have a methyl group. If I start counting from the left, And then on the third carbon, there lies the double bond to oxygen, so it's a ketone, right? So how many carbons in the longest chain? 1, 2, 3, 4, 5. So it's actually pent. And on the third carbon, we have our double bond. So pent 3, or pentanone. Pentanone, yes. Pentan 3 own. Okay, but that's not the only thing that's happening. On the second carbon, we have a methyl group. So 2 methyl pentan 3 own. All right. How many carbons do we have in total? 1, 2, 3, 4, 5, 6. Hydrogen 3, 6, 7, 8, 9, 10, 11, 12. And then we have 1 oxygen. All right. Why am I counting the number of carbons and hydrogens? Well, just in case they want us to talk about or to identify some, what do you call this? Isomers, then it becomes easy for me to identify. Okay. And then G, I am going to rearrange it a bit. I see in my longest chain, I have 1, 2, 3, 4. Okay, I have 4 carbons. So 1, 2, 3, 4 in the in the longest chain, and then my last carbon, I have a double bond to O and then OH. Okay, so that's the 4th carbon. The 3rd carbon, so if I take 1, 2, 3, 4. So the 3rd carbon has 2 methyl groups. Okay, so there it is. 3rd or 2nd? Okay, so yeah. Let me see. No. 2nd. It's the 2nd because just right next to it, 1, 2. Yes, the 2nd. Yeah, just be careful when you're doing it like me. Do not confuse yourself. I just want to see things in a straight line, because the way they put it can be a little bit misleading. So we have a carboxylic acid. It's butanoic acid. First of all, that's one thing we can see, because there are 4 carbons in the longest chain. So butanoic acid. And on the second carbon, this is the first, second, I have 2 methyl groups. So 2, 2 dimethyl butanoic acid. Okay, how many carbons? Well, there are 6 of them. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm seeing 13 hydrogens. No, there is no hydrogen here. What am I doing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 and then 2 oxygens. We're almost there. Whew. You only do this if you have time. Where are we now? 11 minutes. All right, not many minutes left. How many minutes allocated? 19. Okay, so 8 minutes left. H, this one is straightforward. I'm not going to redraw the structure. We have another ketone, but the longest chain has 4 carbons. So this is butane. Butane 2 own. And that's it. There's nothing hectic about it or funny. So we have a C4. H, we have 1, 2, 3, 4, 5, 6, 7, 8. And a O. All right, we have analyzed it as best as we can. Now let's answer the questions. My goodness. All right, so define the term organic compound. So an organic compound is a compound containing carbon atoms, okay? So as long as it has carbon atoms, it is organic. Now it says, write down the IUPAC name of compound E. Do we have the IUPAC name for compound E? Yes, we do. So we're just going to take it from there, copy it in, and we write the answer. Okay, and then 2.2.2, what is the IUPAC name for compound H? We have it there as well, butane 2-one. All right, and then we are there now at question 2.3. So it says write down 2.3.1, write down the structural formula for compound B. I think we already put it there, but we're gonna have to be a little bit elaborate. I'll show you now what I mean by that. Okay, so there we have our ester. Okay, so if they say they want the structural formula, we're gonna have to put in the H's. You cannot just leave it blank. Okay, they can be a little bit of a nuisance, but for those marks, you gladly put them in. And apart from that, it's all good. So for every carbon, there are 4 bonds. For every oxygen, there are 2 bonds. For every hydrogen, there's 1 bond. There it is, the structural formula for compound B. And then the structural formula for compound C. So we already put it there. Let's just fetch it and deliver. All right. So yes, compound C, 4-ethyl, 3,3 difluorohexane. Yes, that's what we have. This is a haloalkane, by the way. Now we're just putting in our hydrogens. Obviously, in an exam situation, you can't copy and paste like I'm doing, but you can take each question as it goes, depending on your speed. So there we have it with all its hydrogens. And now 2.3.3. It says, write down the general formula of the homologous series to which compound E belongs. So compound E, what did we say about it? It's an alkene, all right? And we need to put the general formula for the homologous series. So for an alkene, it's CnH2n, all right? And then now we go to 2.3.4. Now we need to get the structural formula of the functional group of compound F. What did we say about F? We said that F is a ketone, and they want the structural formula of the functional group. So you're not going to put the whole, they already put the structural formula for us, but they just want for the functional group. So for ketones, we know that you have a carbon with a double bond to oxygen somewhere in the middle. Okay, so you could put another C over here, another C over there, or you could have just done it like carbon with a double bond to oxygen, and then you have the R's. Okay, I hope for both you get all the marks. All right, yeah, and then so that would be the main one. Obviously there are some attachments there. hydrogen, I don't know if really that's necessary, but you catch the drift. Okay, and then 2.3.5. So the IUPAC name of the alcohol needed to produce compound B. Remember compound B, that is your ester. We established that the pentyl part is the carboxylic acid, which is pentanoic acid, and then the methanoate, that tells us that our alcohol is methanol. So the IUPAC name of the alcohol needed, or the alcohol required, that is just simply methanol. All right, now 2.4. Yeah, we're not just left with 2 more questions. So it's going by very quickly. Write down the letter or letters of the compounds or compound that is a functional isomer of compound G. So G, remember, is butanoic acid, 2,2 dimethyl butanoic acid, and we know that the functional isomer of carboxylic acid is actually an ester, and the only ester that we have is actually B, right? Pentyl methanoate. And another, also something to look out for, if it is an isomer, we check the formula. So we have C6H12O2. I see it here as well, but they were dealing with the carboxylic acid. They want one with G. So C6H12O2. So yes, we know that G is the functional isomer of B. All right, for 1 mark. And then 2.4.2, it says write down the letters or letter of the compounds or compound that are chain isomers of each other. So if they are chain isomers of each other, they belong to the same functional group, but the arrangement of the atoms is quite different. Okay, one can be branched, one can be straight, etc., etc. So remember, we identified that G is an isomer of B, which is also an isomer of D. And we established that D is an acid, hexanoic acid. G is also an acid, butanoic acid. So I would say G and D, or D and G. They are chain isomers of each other. And then we are done with question 2. I feel like I rushed through it. That's what you do. When you practice these things, you also learn how to deal with your time. And how are we doing for time? 19 minutes. Yeah, we're good. 19.2, so we're good. Question 3. So it says the relationship between boiling point and the molecular mass of aldehydes, carboxylic acids, and primary alcohols is investigated. All right. Curves P, R, and S are obtained. All compounds used are straight chain molecules. All right, so there are no branches over here. Okay, and we can see here that, okay, fine, we have our boiling point that actually, with an increase in molar mass, there's an increase in boiling point, right? And we're also looking at what? We're looking at aldehydes. Okay, also known as what? Carbonyls, right? Okay, and then we also have carboxylic acids as well as primary alcohols. So I'm gonna put alcohols first. Okay, they are hydroxides. All right, and then we have, or from the, let me just say hydroxyl, from the hydroxyl group. And then we have carboxylic acids. Okay, and carboxylic acids, they're basically a combination of carbonyls as well as the hydroxyl group. Okay, and we therefore refer to it as the carboxyl group, combination of carbonyls as well as hydroxyls. Okay, so basically what I'm trying to get to here is the carboxylic acids will definitely have the highest boiling point. Okay, they actually have the strongest intermolecular forces. Then you have alcohols, which are strongest. So stronger. And then you have aldehydes, which are strong. Okay, strong intermolecular forces. All of them are polar. Yeah. So by knowing all of this, you can already tell that P has to be your carboxylic acids, R has to be your alcohol, and S has to be your aldehydes. Okay, so at least you know what's going on. And you can see, like I said, with an increase in molecular mass, you get an increase in boiling point. And the higher boiling point, the stronger your molecular or intermolecular forces, the more energy required to break them, etc. Okay, now let's get to the actual questions. So 3.1, it says define the term boiling point. All right, so boiling point, as you know it, would be the temperature at which your vapor pressure or the vapor pressure of a substance is equal to the atmospheric pressure. All right. And then 3.2, write down the conclusion that can be made for curve P. Okay, so for curve P, all curves, generally, like I said, the boiling point, right, an increase in boiling point is as a result of an increase in molecular mass. Okay, so an increase in molecular mass results in an increase in the boiling point. But if I look at P in particular, because that's the trend for all the graphs, right, for the carboxylic acids, aldehydes, as well as the alcohol, primary alcohol. So that is the general trend. Increase in molecular mass results in an increase in boiling point. But specifically for P, I would say that then P would have to be the carboxylic acid. All right. And now 3.3, it says, explain the answer to question 3.2 in terms of the structure of the compounds. Okay, in terms of the structure of the compounds. Okay, so all these compounds contain London forces. All right, London forces. So for your aldehydes, okay, so for the aldehydes, it's basically your dipole forces. Okay, let me just put it nicely. It's basically your dipole forces, right? Dipole London forces. And then you get your alcohols, which is basically your hydrogen. Hydrogen bonding, London forces. And then you get your carboxylic acids, which is also quite very strong. Your hydrogen, it's a combination, remember? Hydrogen dipole or hydrogen bonding dipole London forces. All right, so, but now they said explain in terms of the structures of the compound. So as a result, with your aldehydes, because it's just a dipole, you have your carbon that is double bonded to oxygen. Okay. And then your alcohol, you have it bonded to the OH group. And then your carboxylic acid, you have a double bond to oxygen and a bond to your OH group. Okay, so hence you have your, now we're specifically focusing on the carboxylic acid. So you are definitely looking at hydrogen bonding, which is very strong. And you also have your dipole over there. All right, so yeah, how else can I say it? Because of that, because it contains both the hydrogen bonding as well as the dipole London forces, P has to be your carboxylic acid, okay? And as a result, looking as well at the structure, you know that it takes a lot of energy to break the bonds, okay? So hence it has a higher boiling point, also a higher melting point if you were to go into detail. All right, and the intermolecular forces are quite strong. They're the strongest. Okay, so that's why P is above, curve P is above all of them, because it is a carboxylic acid. All right, and then we get to 3.4. So I said a whole lot of things for 3.3. You'll just summarize nicely for yourself. Now it says curve R represents the alcohols. Yes, we do know, we did conclude. P is the carboxylic acid, R is the alcohol, and S is the aldehyde. So curve R represents the alcohols. Now 3.4.1, it says which homologous series is represented by curve S. Okay, we have already discussed that again. So basically, the aldehyde. Remember, homologous series, aldehydes. If they said functional group, we would have said the carbonyls. Okay. And then 3.4.2. Explain the answer to question 3.4.1 by referring to the strength of intermolecular forces. All right, so if we know that R is alcohols and we know that P is the carboxylic acid, then S has to be the aldehydes, right? And Y. So in comparison, okay, so we need to just say, yeah, while we're comparing it, so in comparison to curve R and P, so S has, it has weaker intermolecular forces. Okay, so in comparison, they are weaker, although generally they are strong because you have a polar molecule. All right, so with the carbonyl groups, so the London forces are weaker. Okay, so weaker intermolecular forces, like we had said previously, those are your London forces. So it's weaker in comparison to alcohols as well as the carboxylic acids. And really that has to do with the fact that carboxylic acids and alcohols have hydrogen bonding. This is just, it's just polar. Okay, it's polar. It's a dipole. All right, and you need less energy. So less energy is required to break the bonds of aldehydes. Okay, so I would just, how many marks is this? 2 marks. I would leave it there. Then you get 3.5. So it says now for curve R, write down, remember curve R, that's the alcohol. So write down the molecular mass of the compound with a boiling point of 97 degrees. All right, so let's just see. 97, so we have 100 over, I need to make a mark on this sheet. Okay, but yeah, so we need to look at that graph. Okay, let's just see again, 97 degrees. So we need to look at the boiling point there. I see the student took 97 for molar mass. They're supposed to take 97 degrees. But yeah, let's just try to see. So there's 100. I would think 97 is somewhere around there. Okay. Whew. Yeah, not exactly accurate, but you who had the graph paper, you should be able to do well. So it's somewhere around 60. Okay, so we can say that the molar mass of the compound, 3.5.1, I would say 60 grams per mole. All right, and then 3.5.2. Write down the IUPAC name. Ooh, okay. So for curve R, remember that's an alcohol. For the alcohol, you have a carbon attached to a hydrogen, attached to an OH group, and then attached to another carbon. Okay, let's just start there. Okay, so if we have 2 carbons and we have 2 hydrogens and 1 oxygen, so carbon, I think it's 12, the molar mass, and then hydrogen is just 1, oxygen is 16, so yeah, we have 24 plus 2 plus 16, that's what, 32. No, 42. 42, yeah. Okay, so we're not there yet at 60. So let's just add a hydrogen and another hydrogen. I don't know why I just put, yeah. Okay, but that's also not going to get us to 60. So let's add another carbon. Let's say we add another carbon and we close it off here. Okay, so this is doing it the long way. Yeah, so let's just remove all of this and just add everything up. Okay, so we have 3 carbons. We have 1, 2, 3, 4, 5, 6, 7 hydrogens and 1 oxygen. So 3 times 12, which is 36, and 7 times 1, which is just 7, and O, which is 16. Oh, I'm missing another H. Okay, so it's actually 8 hydrogens. All right, so we have 16 over there. Okay, so what is 8 plus 16? That's 24. And 24 plus 36, that gives us 60. Whew. Okay, we finally get to an answer, and it's only 2 marks. My goodness. So the IUPAC name, we have 3 carbons, and it's a primary alcohol, remember? So met it prop, so we have propanol. Okay, there's no need to say propan 1-ol. It's a primary alcohol, it's fine. It's fine as propanol. Okay, we can leave it at that. And then 3.6. So it says 2 compounds A and B used in this investigation have a molar mass of 74 grams per mole. Just note that we have 74 grams per mole. A has a boiling point of 118. B has a boiling point of 142. Explain the difference in these boiling points by referring to the structures of these compounds. All right, so I think this question is not really direct, but since they said in this investigation, I'm tempted to go to the graph and check the boiling point of 118 and 142. So if I had a look at the boiling point of 118, if this is 125, 118, probably somewhere there. Okay. Oh, there. 118, and then we have 74, remember? So this is 80, so 74, probably somewhere there. All right, so 118, I'm there. Okay, and then the other one, let's just check quickly, 142. So I go again, 142, just before 50. Okay, so we are there, 142. Okay, so basically for 142 degrees Celsius, I'm dealing with a carboxylic acid, and for 118 degrees Celsius, I'm dealing with the alcohol. All right, let's go back. So A is 118 and B is 142. So explain the difference in these boiling points by referring to the structures of these compounds. So a carboxylic acid, remember, it has both the carbonyl group as well as the hydroxyl group, okay? And because of that, you're going to have very high intermolecular forces. You're going to need high energy to break them, okay? And this is basically, the structure of it, of a carboxylic acid. And then your alcohol, you basically have the hydroxyl group on it. It also has high intermolecular forces, but they are lower than the carboxylic acid. We also need high energy, but that energy is lower than the carboxylic acid. Okay, so that is the difference. That's why we have a difference in the boiling points. So that's one way you could have answered this question. Another way you could have answered it was to say, here we are given straight chains. Okay, so if you have straight chains, you're going to have a higher boiling point, higher melting point, lower vapor pressure, and so forth. All right, if you have a straight chain. And why is that? It's because the surface area is high. So the higher the surface area, the more energy is going to be required to break the bonds, hence the higher boiling point, higher melting point, etc. Okay, so that could have been the 142 degrees. It was a straight chain. Okay, so that's your B. And then what if you have a branched chain? Okay, so if it's branched, it means that, so therefore, your surface area would actually be low. And if the surface area is low, there's less energy required to overcome or to break the bonds apart. Okay, so therefore, it'll have a lower boiling point, melting point, a little bit of a higher vapor pressure. So yeah, so you could have answered this question looking at the graph, or you could have just talked about the structure, literally like straight chains versus branched chains. And that would explain the difference in the boiling points. And that's it for question 3. Question 4. Okay, we're still there with the organic chemistry. So it says for 4.1, consider the cracking reaction below. Okay, and then 4.1.1. So we have what? 16 carbons, 34 hydrogens. So with cracking, okay, yeah, but I see. The first question says define cracking. So basically cracking is when you have a large saturated hydrocarbon that is broken down into smaller, more useful, unsaturated molecules. All right, so when you break up, or when you crack a hydrocarbon, a saturated hydrocarbon, meaning you're going from an alkane, so yeah, you have written your definition. So basically, in summary, you're going from an alkane, and your product normally has alkanes as well as alkenes, because in the definition, we did say that you want smaller, more useful, unsaturated molecules. So it's a combination of alkanes as well as alkenes. Okay. Breaking apart an alkane to get an alkane and alkene. So 4.1.2 says, write down the values represented by X, Y, and Z in the equation above. So let me just write it down. So we have C16, H34, and then it breaks up to C6, H14, plus C6, and we have HX, plus 2CY, HZ. All right, so in total, we have what? 16 carbons, right? Now, we have used up the 6 and the 12, so now we are left with 4. So over here, I need to have 4, all right? So 2CY has to be 4. So basically, Y is going to be 2, okay? So at least then we can remove that Y and put a 2 there. So we have C2. Okay, now when it comes to X, do you see here we have an alkane? Let me just use a different colored pen. So here we have an alkane. And I see here we still have an alkane. I'm expecting here for us to have alkenes, more useful. Remember, according to the definition, we want smaller, more useful, unsaturated compounds. So I'm going to take those as alkenes. Okay, and if we're going to take it as an alkene, it means then the general formula for an alkene is CnH2n. So we can then get X. Because if C is 6, H has to be 12. We're just going to say 2 times the 6. All right. So in this case, I said Y is 2, and then X would be 12. All right. So we can then already just put the 12 there. Okay. So now let's just see. So on the right side of the arrow, the carbons have now balanced. We have 16. The hydrogens. So on the left, we have 34. On the right, so far we have 14 plus 12. All right, plus 2 times Z. All right, so we know that we need to have 34 in total. Minus 14, we have 20. Minus 12, we have 8. Okay, so Z then has to be equal to 4. All right, so yeah, let's just see. So yeah, we have 4 over there. So does it all add up? Yes, the carbons, they are equal. 16 on each side. The hydrogens, we have 14 plus 12, which is 26. And 26 plus 8 gives us 34. So I believe we are done. So Y is 2, X is 12, Z is 4. That was a nice calculation to do. Yeah. Now it says compound C6H14 undergoes complete combustion. All right. Remember, whenever you have combustion, you have your hydrocarbon. Okay. In this case, an alkane. So yeah, let me just write it down. So your alkane plus oxygen gives you carbon dioxide plus water. Okay, so yeah, that is the whole concept of combustion. Now it says for 4.1.3, using molecular formulae, write down the balanced equation for this reaction. So we have C6H14 plus O2. Let me give us some space there. Plus O2 gives us CO2 plus H2O. All right. So currently we have 6 carbons. And over here we have 1, so we can put 6 there. So I can see now I have 6 carbons. And then hydrogens, I have 14 on the left. And on the right, well, I need to put a 7 there in order to get 14, so we're good. Let me just... And then oxygen. So over here we have 2. And oxygen's this side. What do we have? We have 12 plus 7, that's 19. Okay. So we have 2 here and we have 19. All right, so I can't, there are already 2 here. So 19 divided by 2 is like what? 9.5. Okay, I can't really put 9.5 there. I need to multiply everything by 2 throughout in order for it to balance. Okay, so if I multiply by 2, I'm going to have 19 here. If I multiply by 2, there's the 2. And if I multiply by 2 this side, I'm going to have 12. And here I'm going to have to have 14. So let's start again and see if everything has balanced. Okay, then we can be at ease. So carbon, I have 12 over here. This side I have 12 as well. Hydrogen, I have 2 times 14, which is 28. And on the other side, 14 times 2, that's also 28. Oxygen, I have 19 times 2, which is what, 38. And then on the other side, I have 12 times 2, which is 24, plus 14. So that is 38. Okay, then I'm glad this is balanced. How many marks? 3 marks. I think that is fair. And now we get to 4.2. So it says, consider the equations for the reactions 1 to 3 below. A and B represent organic compounds that are positional isomers, okay? And X is an inorganic compound. So let's just, before we even answer the question, let's just have a look. What do we have for 1? I'm going to draw the structural formula. So it's CH3, CH2, and then we have CH. Then we have another CH, so that's a double bond. And then CH3. Alrighty, and then we're adding hydrochloric acid, or just say hydrogen chloride. Alright, so in adding it, this is an addition reaction, by the way. So what kind of addition reaction is this? This is hydrohalogenation, because there's a hydrogen and there's also a halogen, so hydrohalogenation. And what do we normally get as a product? So we're going to get a haloalkane as a product. Normally I would stop right here, but we have A and B as products. This haloalkane that we normally put there, it's normally the major product, okay? But because we have A and B, and they told us that A and B are positional isomers, we will have to then put the major as well as the minor. Okay. Yeah, we will have to put the major as well as the minor products. And which one is major and which one is minor? Okay, let's just firstly have a look. How do we then first initially get the major product? So you're going to have to use Markovnikov's rule. And what does Markovnikov say? He said that for the major product, you're going to have to go look at which carbon has more hydrogen atoms. The one that has more hydrogen atoms, there you place your hydrogen. That is the major product. Okay, so if I look here, this carbon has 1, this carbon has 1. So let's go to the next one. That carbon has 3. So I know then that I'm going to place my hydrogen over here. Okay, that is my major product. Okay, I see I don't have space, so I'm just going to say the major product, and this will be plus the minor. All right, so which one is my major, which one is my minor? If I draw again the structural formula, 1, 2, 3, 4, 5. So we have pentene there. Pentene, yeah, pent-2-ene, if you like. So now we don't have double bonds anymore. We have a haloalkane. And I said for the major product, your hydrogen is going to be there. Putting in these hydrogens is such a pain. Okay, and if you put a hydrogen there, it means the chlorine is going to come here. Okay, so this is basically 2-chloropentane. No, what am I saying? 3-chloropentane. So this is our major product. And which one is our minor? Okay, so this is the major, and then our minor, 1, 2, 3, 4, 5. The minor one, well, the hydrogen goes there, meaning the chlorine will go there, and you can put the rest of the hydrogens. I'm not going to put it here. We're not required at the moment. We're just analyzing this. So yes, one is A, the other is B. I don't know which is which, but probably step 2 will give us an indication. So now we have A, okay, and it's a haloalkane, by the way. Okay, so we have our haloalkane. Okay, haloalkane, it's fully saturated. So we're looking now at what? At a substitution reaction. I see water there, so it's probably hydrolysis. We don't know, but the product is water. No, not water. It's an alcohol. There's an OH group. Okay, hydrolysis is what is going under. Okay, so we have CH3, CH2, another CH2, then we have a CH and an OH, and we have CH3. Alrighty, so now we see the OH, where it went. Okay, so basically, this then would have to be A. So this is A, our minor product. B is our major product. Okay, so it is clearer now which is which. And after it goes under hydrolysis, what would be X? Okay, so we have substituted chlorine for the hydroxyl, okay, hydroxide. Okay, so now we have a remaining H and Cl. So now we have HCl, and that is what X is. So that's X. We have A, we have B, which is great. And then thirdly, so basically we have our alcohol. Looks like a secondary alcohol. All right. So that alcohol, I'm not going to write the structural formula. So the alcohol then becomes another alkene. So we have an alkene here. Let me just put this CH3, CH2, CH, double bond CH, and then CH3. So we are back to where we started. Oh, yes, we are. So it's pent-2-ene plus water. Okay, so basically, if on the second step we say this is hydrolysis, this is a substitution reaction. If we take alcohol and we go back to an alkene, we basically took out the water, né? We dehydrated it. So this is dehydration. Dehydration reaction, this is an elimination reaction. Elimination reaction. Okay, so we have, sort of like broken down what's actually happening. Now we can move along with confidence and answer the questions. All right, by the way, this is out of how many marks? 19 marks. Let me just see, 19 times 1,2. How many minutes should I be spending here? 22,8 minutes. Where am I now? 15 minutes, so there's still time. All right, so write down the definition of positional isomers. Okay, so remember an isomer by definition has same molecular formula but different structural formula, right? But in this case with positional isomers, so basically you still have the same molecular formula but different positions, okay, but different positions of either side chains if you have side chains, substituents if you have any, or functional group in the parent chain. So you have your parent chain, but then there are different positions there, okay? And we can see over here where the chlorine is. Initially, for your major product, the chlorine was on the 3rd carbon, but for your minor product, it's on the 2nd carbon. So that is the definition of positional isomer. Isomers. And 4.2.2, this is the type of reaction represented by reaction 1. Okay, so we did say it's an addition reaction, also known as hydrohalogenation. So you can decide, are you going to write addition reaction or are you going to write that one is more nicer, hydrohalogenation. Hydrohalogenation reaction. Okay, 4.2.3. Now write down the structural formula of compound B. So compound B is our major product with the chlorine is on the 3rd carbon. So we can put it there, 1, 2, 3, 4, 5. I should have actually just copied it. Why am I working too hard now all of a sudden? So this is what B is. Copy and paste. We thank God for technology. Do things much quicker. Okay, so they just want the structural formula. All right, that's it. They didn't want the name. If they did, it would be what? 3-chloropentane. All right, and then 4.2.4. So formula of X. So X, we did say that it's hydrogen chloride, right? And then 4.2.5. The inorganic, write down the inorganic reagent for reaction 3. So for dehydration, this is just dehydration. Ne? We took out H2O. No, it's a dehydrohalogenation. You took out, so from your alcohol, this is just dehydration. There's no halogen there. Okay, so dehydration. What are they asking again? The inorganic reagent for reaction 3. So this is concentrated sulfuric acid, or you could have said H3. I always forget the name. H3PO4. Okay, and then now it says compound A compound A, the haloalkane, can be converted directly to the organic product of reaction 3. Okay, so the organic compound, so you can then go, what are they saying? 4.2.6. So they're saying you can go from the haloalkane all the way to an alkene. Okay, so you've sort of removed the hydrohalogen, okay, because the product doesn't have the halogen anymore, but it's just a double bond there, an alkene. Okay, so now for 4.2.6, it says, besides heat, write down the reaction condition needed for this conversion. What is this conversion again? We're going from a haloalkane to an alkene, so we have removed a hydrogen halide. So what do we need then? You could say, apart from heat, we can have another reaction condition, concentrated strong base, either potassium hydroxide or sodium hydroxide. And then 4.2.7, write down two terms that describe this type of reaction. Okay, so basically we have removed a hydrogen halide, so we can call it dehydrohalogenation, or we could say this is an elimination reaction. Those are the two terms, elimination reaction. Okay, and that's it for question 4. How much time did we spend? 20 minutes. Not so bad. All right, we are halfway there. So we're going to look at the topic of rates of reaction. And let's read what it says. The reaction between excess dilute hydrochloric acid and sodium thiosulfate is used to investigate factors that influence the reaction rate. You know, those factors like surface area, concentration, temperature, etc. Okay, and since we have excess dilute hydrochloric acid, it tells us that the sodium thiosulfate is the one that's limiting here. That's the limiting reagent. So we have there the balanced formula, a chemical formula. And now it says the concentration of hydrochloric acid, or HCl, used is 1 mole per cubic decimeter. All right, so they gave us the concentration. I don't know if we're going to use it, but yeah, let's just note it. That's just 1 mole per cubic decimeter. The same volume of hydrochloric acid is used in each run. Okay, so if we had 10 cubic decimeters, it's going to be 10 throughout. All right. But I'm not saying it's 10, I'm just saying as an example. So it says the time taken for the cross on the paper under the flask to become invisible is measured. So I've covered rates of reaction, practically how do we measure it. If you check out the playlist, the chemistry playlist, you'll find it. And so the whole thing with this experiment is the quicker the X disappears, the quicker the rate of the reaction, or the high, or that indicates how high the rate of reaction is. If it takes very long for X to disappear, then the reaction rate is quite slow. Okay, so that's the whole thing about this. And we take the time, we measure the time it takes for X to disappear. All right, so basically whatever it is that you're changing here, on your y-axis, that's the dependent variable. That's where we put time, okay, per rate, per time. That's what you're going to put on your y-axis. But let's read further to see what is varied, so that we can see what we can put on the x-axis should we plot a graph. All right, so the table below summarizes the reaction conditions and results of the experiment. So we see run 1, we have the volume of sodium thiosulfate, we have the volume of water, the concentration, as well as the time. All right, and we see for run 1, this is the initial concentration, or the original concentration, before there's any kind of dilution. I say that because we keep adding water, so that dilutes the entire thing, and we see that the concentration decreases. So run 1, where you have your original concentration, is 0.13. Run 2, it's 0.1. So it keeps reducing as you add more water, right? It's becoming diluted. And what happens to the time? If you are diluting it, remember, the higher the concentration, the higher the rate of the reaction. So if the concentration is reducing, we will see it then with the time as well. It takes longer for that X to disappear. Another thing about that X disappearing, what makes it disappear? If you look at the products that form, you'll see that we have a precipitate, which is sulfur. All right. So the milkiness or the turbidity that causes the X to disappear is due to that precipitate called sulfur, and it's yellowish in color. Okay. So we sort of know what's going on. Now we can get to the questions. All right, so 5.1, define reaction rate. Simply put, the rate at which the reaction takes. But you're not going to say that, nor are you going to write that. So the rate of the reaction is basically the change in amount of what? It could be amount of concentration, could be an amount of mass, it could be amount of moles, etc. So basically it's the change in the amount, I'll use concentration for now, change in the amount of concentration of your reactants or the concentration of your products per unit time. All right, as soon as you have the word rate, time has to be involved. Okay, so that's the definition. You'll get that for 2 marks. And then it says, write down the independent variable for this investigation. I already told you our dependent variable will be time, or 1 over time. Okay, so what is it that we are changing that eventually gives us the time? We are actually changing the concentration. Remember, concentration is one of the factors that influence the reaction rate. Okay, so we see here from the table that as you reduce, or as the concentration is being reduced due to the addition of water or due to diluting, then the time increases. Okay, so the independent variable in this case then would be concentration. All right, now 5.3. Calculate the value of P in the table. All right, so basically we're looking for the concentration of sodium thiosulfate for run 3. Okay, this, yeah. So remember for run 1, okay, we know that our concentration, which is the original concentration, is 0.13 mole per cubic decimeters. No, yeah, per cubic decimeters. Okay, now what happens in run 2? What if P was there by run 2? What we could have done, we know that the initial concentration of 40 cubic centimeters, it's still 0.13. It's just now we have water that's added. Okay. Sorry, just need to answer a call. Sorry about that. Okay, yes, now I don't even know where I was, but looking at run 2, if we use the formula, so we know that the number of moles for sodium thiosulfate, that won't change. Irrespective of us diluting, that will not change. So if we say the number of moles initially is equal to the number of moles finally, we can then say number of moles. Remember the formula concentration is number of moles over volume. So number of moles would then be concentration times volume. Okay, so initially and then finally. All right, so this is run 2. I'm trying to show you how we can get that 0.1 so that we can use the same concept to go and calculate what P is. So I'm just doing extra stuff. So the initial concentration, which we said, doesn't stop, or it doesn't change, rather. We have 0.13, right? And the volume there that's applicable is 40 cubic centimeters. I'm going to leave it as 40 because it will cancel out. Oh, you know what? Let's just stick to cubic decimeters. It's fine. You can do that. And then we're trying to get this concentration over here for run 2, right? Let me just put it as 2. And then what's the volume there? Well, the volume we have 40, right? But we have to look at the total volume. We also have 10 cubic centimeters of water. Okay, so let me be consistent. 40 plus 10, all of this is times 10 to the power negative 3. Okay, so if I were to then get the concentration of run 2, what would that be equal to? So I have 0,13 multiplied by 40 times 10 to the negative 3 all over 50 times 10 to the negative 3. Okay, and you see, I don't like the way this is written. Let me just see if I can change it. If I say shift mode, and I don't want it in scientific notation, let's say, yeah. Okay, let's see if that will change things a bit. So 0,13 times 40 times 10 to the negative 3 all over 50 times 10 to the negative 3. Even worse. Okay, what did I do now? Oh, negative. Okay, I get 0,104. Okay, sorry, let me just try this again. And let's see if that will help. Normal mode. Okay, I'm sorry about this. This is taking too long unnecessarily. Yes, so we have 0,104, and if I round it off, we get the 0,10. So you see what we're going to do. Now for run 3, there are 2 ways you can do it. Okay, so we're saying our initial concentration still 0,13. Okay, that has not been diluted, but what amount of it is the volume of thiosulfate? It's actually 30. I'm just going to leave it as 30. And we're looking for P, the concentration, right? And our volume will be 30 plus 20. Okay, so P therefore is 0,13 times 30 divided by 50. And what do we get then? 0,13 times 30 divided by 50. And that is 0,078. If we round it off, we then say it's 0,08, and that is mole per cubic decimeter. Okay, so that is the answer for P. That is the concentration for the third run. All right. What you could have also done is you could have taken run 2's answer. Okay, this is now more information. So that's 0,104. That's the concentration, but you're still using the volume that's applicable for the third run. Okay, and then instead of 50 though, the volume for the second run is 40. Okay, so you're going to say 30 plus 10. Okay, 30 plus 10, and therefore P would have been 0,104 multiplied by 30 over 40. That should also give you the same answer. But I hope you see the trend here. If you don't fully understand what I'm doing, you can comment below, and yeah, I'll try to explain it. But I was just trying to show you different ways of doing it. Okay, so basically P is 0,08 moles per cubic decimeters. And are we expecting a low answer, a low concentration? We are. If you're getting anything more than 0,1 or 0,13, it's wrong. That's because the time is still increasing. So if the time is increasing, it means your concentration is decreasing. Okay. now we get to 5.4. It says, when 0.21 grams of sulfur has formed in run 1, the cross becomes invisible. Okay, and we know that how long does it take for it to become invisible? It takes 20.4 seconds. So now it says, calculate the average reaction rate with respect to sodium thiosulfate in grams per second. So basically, our reaction rate or rate of reaction will be equal. And in this case, we can see that, it's going to be the change in the mass over the change in time. Okay, and in this case, I mean, our reaction rate is, it's decreasing. Yes, not that our time is decreasing, our time is increasing, but our rate of reaction is actually decreasing. Okay, so we must put a negative here. Okay, because it's taking much slower to see or to get rid or for the X to disappear. So if it was quicker, then our rate of reaction put a positive, but now it's just decreasing, so we're putting a negative there. Okay, so now we need the mass. All right, so they've given us the mass of sulfur. So what we can do, we can get the number of moles for sulfur with this mass that has been given. Okay, so the mass is 0.21 grams, and the molar mass for sulfur, if you look at your periodic table of elements, that should be, so sulfur, we get 32 grams per mole. Okay, so we can then get the number of mole for sulfur. Let's just get back to the question. Okay, so the number of mole is equal to your mass over your molar mass. Okay, your mass is 0.21 grams and your molar mass is 32. All right, so 0.21 divided by 32 gives us an answer of 0.0065625, or you could have just said 6,5625 times 10 to the power negative 3 mole. Now, if we have a look at our balanced chemical formula, we see that we have 1 mole for sulfur as well as 1 mole for sodium thiosulfate. So actually, this is also equal. This is the number of mole for sulfur. This is also the number of mole for sodium thiosulfate. Okay, so that's cool. We have the number of mole. Now what can we do with that? We can actually get the mass, therefore, of sodium thiosulfate. So the mass, if number of mole is mass over molar mass, the mass will be number of mole of sodium thiosulfate multiplied by its molar mass. Okay, so now we need to get the molar mass. Let's just get it up here. So we have 2 of the sodium plus 2 of the sulfur plus 3 of the oxygen. So what is sodium? I think it's about 23. So 2 times 23 plus 2 times 16, right? That's for sulfur. No, 32. 16 is oxygen. Sulfur is 32 and 3 times oxygen, which is 16. So the molar mass of sodium thiosulfate will be 2 times 23 plus 2 times 32 plus 3 times 16, and that is 158 grams per mole. So now we have the number of the number of mole, or the mole. So 6,5625 times 10 to the negative 3 multiplied by the molar mass, which is 158. And what does that give us? I'm just going to say 0.21. I don't want to rewrite the entire thing lest I miss a number. So multiplied by 158. So I see here we get 1,0, 36875. Just going to round it off to 1,04 grams. Now, this mass of sodium thiosulfate is actually a theoretical mass. And I don't know how strict they are in you using the theoretical versus the actual. So, yeah. Okay, and I'm saying this because we know that our limiting reagent here is sodium thiosulfate. So let's just check. Let's just be sure. Okay, we know that mass is number of moles times molar mass, and number of mole is concentration times volume times molar mass. So this is now the theoretical one. The theoretical values are normally more than the actual values because they are sort of ideal, if I could say. But the actual one is the one that you actually want to use. Okay, so what is the concentration then? Initially it was 0,13. The volume was 50 cubic centimeters, which is just 50 times 10 to the negative 3 cubic decimeters. And the molar mass is 158. So let's just see. 0,13 multiplied by 50 to the negative 3 multiplied by 158. So here we get 1,027 grams. In all honesty, I don't think they would, whether you're going to use the theoretical or the actual, just choose one. I think you're still going to get the same answer. Honestly speaking, we can try both out and see what answer we get. But I think the difference is not that big. It's sort of negligible unless if they ask you to calculate, you know, what is it, percent purity or something, then yeah, it would matter. But in this case, I think it's fine. I think it's okay. So let's just say we use the actual, okay? So remember the final, this sodium thiosulfate is going to be used up at the end. So the final mass will be 0. And the initial mass is the 1,027. And that is divided by 20,4. Okay, so the reaction or the rate of the reaction, I'm just going to say 1,027 divided by 20,4. And we get, rounding off to 2 decimal places, 0,05 grams per second, which is what they wanted, right? Let's say we used the theoretical value, which is 1,04. 1,04 divided by 20,4. We also get 0,05. So the answer is still the same. The reaction rate, whether you use the actual or the theoretical, I think at the end of the day, they will give you the marks. I hope. All right, so that's 5.4. Now 5.5, it says another investigation is performed at different temperatures. Sketch the Maxwell-Boltzmann distribution curve for the reaction at 20 degrees. Label this curve as A. On the same set of axes, draw the curve that will be obtained at 35 degrees Celsius and label it as B. Okay, so our Maxwell-Boltzmann distribution curve looks something like this. So on the x-axis, we actually have kinetic energy. Okay, so I'm just going to say kinetic energy. Okay, in joules or whatever. And then on the y-axis, you have the number of particles. Okay, let me just write it. So number of particles. All right, so when it comes to your graph, I'm going to just label this as A. This is your Maxwell-Boltzmann graph. All right, and over here, I'm just going to put a straight line. That's where you have your activation energy. just going to label it as EA. So once particles pass this point, and you have the shaded area right there, basically the reaction can occur, all right? Your reaction rate is also increased once it passes that point. Yeah, so this is now A. As they said, we should label it. Now, B, A is at 20 degrees, right? B is at 35 degrees. So basically what happens when we increase the temperature? All right, so your graph for B, let me choose a different color. Your graph for B, still starting over there, it will be flatter. Oh, no, start again. Okay. It will be flatter. But now you see there will be more particles that are, actually no, you still have the same amount of particles. So the thing with an increase in temperature, the area below the graph is still the same. Okay, so you still have the same number of particles, but the particles that have actually gone past the activation energy, they now have more energy, more kinetic energy, okay, and effective collision can occur at that point in time. So this is B, okay. All right, so yeah, this is basically how that graph looks. Again, I covered this. If you check out the playlist, the chemistry playlist, you'll see the video where I covered that lesson. All right, so now that's it for 5.5. Let's go to 5.6. Okay, now it says, explain the effect of temperature on the reaction rate in terms of the collision theory. Okay, so what happens then? So you increase the temperature, right? As a result of increasing the temperature, then the particles that you have will actually have an increased kinetic energy. And that increased kinetic energy is actually larger than your activation energy. And therefore, you will have more effective collisions. Okay, the orientation of the particles, the way that they collide, it will be more effective. So we have more effective collisions. Is it double L or double S? I think double. Okay, more effective collisions, and then yeah, more effective collisions per unit time, which is what we want, and as a result, therefore, you have an increased rate of reaction. Okay, and that is how we can relate that. And with that, we are done with this question. See you question 6. Question 6, we are at the chemical equilibrium section of the paper. This now says, consider the following hypothetical reaction reaching equilibrium in a 4 cubic decimeter closed container at 150 degrees Celsius. All right, so basically what we have here is the volume, and then we have the temperature as well. We have our reactants over here, and these are our products. Well, if you're looking at the forward reaction. All right, then it says the graph below shows the changes in the amounts of reactants and products over time. So let's just look at the graph and just analyze what's happening. So we see our reactant AB, it goes down, right? Which makes sense. If products are to form, then the reactants have to go down. And we see that the products start with 0. Okay. And then they reach equilibrium at around 40 to just before 80. Okay, so equilibrium is reached. And then there's a disturbance to this equilibrium. All right, we have a sharp increase in compound A2. All right, and looking at our y-axis, number of moles versus time, so we have an increase in the number of moles for A. Okay. And then, because there's a disturbance to the equilibrium, Le Chatelier comes in and says, whoa, we need to just sort this disturbance out so that we get back to a new equilibrium, and we see that our reactant, so it basically is reactant favored because one of the products increased, so it had to be reactant favored. AB starts increasing gently, as well as B decreasing gently after that sharp increase of A. And then we get to another equilibrium. We can say between 100 and 130 degrees. We have equilibrium there. Then there's another disturbance. Okay, so if it's a sharp increase, we're expecting a change in concentration or number of moles or pressure. But if it's a gradual increase, then it has to do with temperature. Now, we don't know whether this reaction is endothermic or is it exothermic. We don't know. So because of that, I can't tell if there's an increase in temperature or not. Okay, there are different scenarios. Like, for example, if you have an endothermic reaction, it means that an increase in temperature will favor the forward reaction, but a decrease in temperature will favor the reverse reaction. Okay, but if you have an exothermic scenario here, then an increase in temperature will favor the reverse reaction, whereas a decrease in temperature will favor the forward reaction. Okay, so this is for exo, this is for endo. So we don't know really much there, so let's just, not focus too much on it. And let's go to 6.1. So it says, write down the meaning of the term reversible reaction. That's basically, it's a reaction where products can be converted back to reactants. Okay, they're reversible. And 6.2, state Le Chatelier's principle. That's something you should know. I briefly described it as we were looking at this graph. But basically, when the equilibrium in a closed system, remember, closed container, closed system. So when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. Okay, so that's Le Chatelier's principle. Now 6.3 says a change was made to the equilibrium mixture at 80 seconds. All right, we did discuss it. Now it says write down the change. So basically we have a sharp increase, okay, in the number of moles for A2, product A2, okay, the gas. And then 6.3.2 says, use Le Chatelier's principle to explain how the system reacts to this change. So we have our reactants, right? And then we have our products. So now we had an increase in our product. So remember that seesaw that I normally draw? We have our reactants, we have our products. So now P, one of the products, gains weight. If it gains weight, so we have an increase in A2. If it gains weight, it's going to look something like this. Okay, now our products are going to be very heavy. So what does Le Chatelier say? Le Chatelier says, we need to restore this equilibrium. So we're going to favor the reactants. Okay, so then with an increase in the product, Le Chatelier says we need to favor the reactant, so favor the reverse reaction. Okay, favor the reactants or reverse reaction in order to get a new equilibrium. All right, so that is what basically happens. And then in order to favor the reactants, some of the products need to now lose weight. So the products will end up decreasing, right, gradually, and we can see that, okay, that A goes down, B also goes down. Okay, so eventually you have a slight decrease in the number of moles for the products and an increase in the reactants, and therefore a new equilibrium is reached. Okay, So you'll find a way to write it out quite nicely. And then now we get to 6.4. So it says, calculate the equilibrium constant Kc at 120 seconds. Okay, so with this, I don't really know. I mean, it's 4 marks. I don't know if it's necessary to draw the rise table, rise C. So our reactants, we have AB. Our products, we have A2 and B2. Okay, I'm just going to draw the rise table. Although we can actually see from the graph at equilibrium what the number of moles are. Okay, so everything here I'm going to put in terms of number of moles. All right, so the ratio, if we just go back, so it's just 2 over here, 1 and 1. Okay, and then I am just going to go straight to equilibrium. So at 120 seconds, so this is what we're focusing on. For B, I see we have 2. For A, we have 8. And for AB, we have 10. Okay, let's look at what happened initially. So with initial amounts, you're going to just look at 80. Okay, because that's where, or just before 80, where there was, actually at 80. Okay, the previous scenario, what was happening before. So we can see for B, we have 4. All right, for A, it is 10 moles, and AB is at that point 6 moles. All right, and then we can see the change as well, which is why I think I shouldn't actually be drawing this rise table, but this is the change. Okay, yeah, the difference in number of moles. So basically for B, there's a difference of 2. All right, for A, there is a difference. This is basically the difference. It's also a difference of 2. And for AB, where is AB again? There it is. So there's a difference here of from 6 to 10, that's 4. And that makes sense, guys. Why? Because initially you had 6, okay? And then plus 4, you get 10. 10 minus 2, you get 8. 4 minus 2, you get 2. Okay. Now, we have all of this in terms of mole. We need to get this in terms of concentration. So we're going to remember concentration is equal to number of mole divided by volume. So then the volume is 4, right? So 10 divided by 4, that's simply 2.5. 8 divided by 4, that is 2. And then 2 divided by 4, that is 1/2. All right, so we have our concentrations at equilibrium. Now we can calculate. That's why I think it wasn't really necessary to do the table. You could have just read off the values and just calculated from then on. So remember, the Kc value is the concentration of the products divided by the concentration of the reactants. Now, what are the products again? We have A2 and we also have B2, and we're dividing it by our reactants, which is AB squared. Okay, so A2, we have 2, B2 is 1/2, so 2 times 1/2, that's just 1. And then AB is 2.5, that's 2.5 squared. So now if I say 2 times 1/2 divided by 2.5 squared, I get an answer of 0.16. Okay, so that's the Kc value for 4 marks. And then 6.5, let's just go a bit up. So it says at temperature, how do I say temperature? At time 130 seconds, the temperature of the system is decreased to 150. Remember, initially, the initial temperature is 150 degrees. Okay, so now it went down to 100 degrees. So then what can we say about this decrease in temperature? Because we see that when the temperature was decreased, the reverse reaction was favored, okay? Whereas the forward reaction was not favored. Now remember those conditions that I said before. Let's just copy it and see what is actually applicable here. And we can then take it with us. And we can decide whether the forward reaction is exothermic or endothermic. So let's just put this over here for ourselves in a bubble and then answer the questions. Okay, so basically the decrease in temperature favors the forward reaction. So do you see that we have this scenario here? Decrease in temperature favors the forward reaction. So hence, we then know that our delta H is bigger than 0. Okay, it's endothermic, which favors the reverse reaction. So that's great. We know it. Now we can go and answer questions. So now, 6.5.1, it says, draw a potential energy diagram for this reaction. So basically, if they don't specify, we're just going to go with the forward reaction, right? So this is, the whole thing is endothermic, basically, yeah. So what we're going to do, we're going to draw a graph for an endothermic scenario. Okay, so with an endothermic scenario, we know that we have, what do you call this? Potential energy on the y-axis. I'm just going to say EP, and that's in kilojoules. And then we have time over here. We're just going to say that's in seconds. And then we can draw the graph. So basically, it's going to look something like that. Okay. And with that, we know that we have our reactant here, AB. And then there we have A2 plus B2. Okay. And the difference there really is the enthalpy, which we know is bigger than 0. Okay, so this is for an endothermic reaction. Okay, so there we go. Let me just do that again. So endothermic reaction. All right, so that is what, worth 3 marks. That's a nice 3 marks to get there. 6.5.2. So it says, will the equilibrium constant at 100 degrees be greater than, less than, or equal to? Again, let's just remind ourselves, we have concentration of products over concentration of reactants. With this decrease in temperature, the reactants were favored. So if we increase reactants, it means that our Kc value will be less than. It would have decreased. If you increase reactants, Kc decreases. So yeah, will the equilibrium constant Kc, yeah, so at 100 degrees it will be less than the Kc constant at 150 degrees. And how do we explain that? Well, basically, as we have noted from the graph, that with the decrease in temperature, we saw that AB, which is a reactant, okay, increased in the number of moles. All right, and we know as well that Kc, the equilibrium constant, well, that is temperature dependent, okay? Kc is temperature dependent, so only temperature can affect Kc. All right, so we saw that with the reduction in temperature, the reactants, the number of moles for the reactants AB increased, and as a result, with reactants being the denominator, well, we could say that the Kc value is inversely proportional to the concentration of reactants, and as a result, if the reactants increase, the Kc value will end up decreasing. Okay, so we can leave it at that. And then 6.6, we're at the last question. All right, so it says, the initial reaction now takes place in the presence of a catalyst at 150 degrees Celsius. Now, describe the changes that will be observed on the graph between time 0 seconds and 60 seconds. Okay, so I'm just going to increase the thickness of the pen, and let's use blue now. So we are focusing here. So what we can actually conclude here is that, first of all, a catalyst doesn't affect equilibrium. It doesn't disturb equilibrium. Okay, so equilibrium will still be at 6 for AB, and it'll still be at 4 for A2 and B2. Okay, so that's one thing we must just recognize or just note. So a catalyst will not disturb. Okay, so a catalyst will not disturb. Okay, a catalyst will not disturb equilibrium. Okay, that's one thing. Ooh, my handwriting is a little bit equilibrium. All right, that's the first thing to note. But now what about, just looking at the steepness of the graphs. So what will happen now with the catalyst? The number of moles also, you're going to have 12 initially, you're going to have 0 for the products initially, but for it to reach equilibrium will be reached faster. Okay, so what do I mean? I mean that it will probably be steeper over here, and then you reach equilibrium much quicker. Okay, even here, you reach equilibrium much quicker. Whether it's at 10 seconds or earlier than 10 seconds, it is what it is. Equilibrium will be reached earlier. So equilibrium, yes, will be reached earlier. Okay, that's another thing that we can say. And the graphs are steeper. So the graphs for the reactants and products are steeper. Okay, so that is what we're recognizing over here. Again, catalyst will not disturb equilibrium, so equilibrium will be reached 6 moles for reactant AB, 4 moles for products A2 and B2. Secondly, equilibrium will be reached much earlier. Thirdly, what do we observe? The graphs for the reactants as well as the products, they are more steeper. Okay, because what does a catalyst do? It increases the reaction rate, and we see that by graphs being more steep. Okay, and I think that is it for question 6. Thank you. We'll continue with question 7. Question 7. All right, this is the third last question. I keep forgetting that chemistry has 9 questions instead of 10. But yeah, so this is the acids and bases section. It can get a little bit tricky. But when you understand what's happening and what the process and procedure is, then the calculations become a bit easy. All right, so it says to identify metal M in an unknown metal carbonate, the following procedure is carried out. So we have this metal carbonate. Now you know that a carbonate has a charge of 2 minus. So this metal here, it means it has a charge of 2 plus. Okay, because we don't have a 2 as a subscript. So it tells us that this is from group 2. Okay, so all the metals from group 2, beryllium, magnesium, calcium, strontium, barium, radium, those are candidates, okay, for this particular M. Anyway, we have step 1. So they tell us that we have 0.198 gram of this impure metal carbonate, and then it reacts with 25 cubic centimeters of 0.4 mole per cubic decimeters nitric acid. Okay, so step 1, in the initial stages. Okay, so for this nitric acid, we have a volume of 25 times 10 to the negative 3 cubic decimeters. All right, and we have a concentration of 0.4 mole per cubic decimeters. Okay, and also for this impure metal carbonate, we know that the mass is 0.198 grams. Okay, so this is impure. All right, so these are the initial conditions. And then these two, they react. Okay, so we have a reaction that occurs and whatever happens there. And then in step 2, the excess nitric acid is then neutralized with barium hydroxide. Okay, so we have the initial amounts, then this metal carbonate and this strong acid, nitric acid, they react. Then during the reaction, probably the metal carbonate finishes. Then you have excess nitric acid. So it was an excess, meaning that this metal carbonate is our limiting reagent. Okay, so the reaction happened, blah, 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 blah. And then when you have the excess, okay, so some of the nitric acid was remaining. So we have some information there. They tell us, actually we don't know. We don't know anything about that nitric acid, but we do know that this nitric acid, this strong acid, reacted with a strong base, okay, which is barium hydroxide. Remember, hydroxide has a charge of -1, so that's why we have two of them. Okay, and this barium hydroxide, we know that the volume there is 20 cubic centimeters, which will be 20 times 10 to the negative 3 cubic decimeters. And the concentration thereof is 0.15 mole per cubic decimeters. All right. So yeah, you have an initial amount of nitric acid. It forms part of the reaction. There's a little bit left. We use that to neutralize barium hydroxide. Strong acid, strong base, they neutralize each other. pH probably around 7 of this whole neutralization reaction. Okay, so yeah. Now we have summarized information. Now it says, assume that the volumes are additive. And then they give us the reactions that take place. So we can see then for the step 1, we have, I'm just going to put that in a different pen. So we have 2 mole. Okay, so if I were to put HNO3, the number of mole there, a number of mole of this metal carbonate. So the ratio that we have there, we have a 2:1 ratio. Okay, and then if we look at step 2 with the excess nitric acid, we also have a 2:1 ratio. So also number of mole for the nitric acid, a number of mole for the barium hydroxide. So it also has a 2:1 ratio. Right. Yes. It does have a 2:1 ratio. Okay. So that's where the equations help us. Now let's start answering the questions. Okay, so 7.1 says define the term strong base. Okay, so a strong base is strong. It's a base basically that dissociates completely. Okay, unlike a weak base, it doesn't dissociate completely. So a strong base, it dissociates almost completely or completely to form hydroxide ions when in solution. Okay, sometimes they say when in water. I think let's just be safe by saying when in solution. Okay, so it dissociates completely to form hydroxyl ions or hydroxide ions when in solution. Okay, so that is that. 7.2, it says, point 1, calculate the number of moles of barium hydroxide that reacted with the excess nitric acid. So number of mole, well, firstly, concentration is equal to number of mole over volume. Therefore, the number of mole for the barium hydroxide is equal to the concentration times the volume. We know the concentration, it's 0.15, and we know the volume as well, it's 20 times 10 to the power negative 3. So then we can calculate. So 0.15 times 20 times 10 to the negative 3, and that gives us 0.003, or we could just say 3 times 10 to the negative 3 mole. Okay, so that is a nice 3 marks over there. And then 7.2.2. Now it says calculate the pH of the solution after step 1. Okay, so remember with step 1 we have our nitric acid reacting with the metal carbonate. All right, so we have our initial condition, we have the reaction, and then we have the excess. Okay, so in order for us to get the pH of the solution after step 1, basically, yeah, so the pH, since we have excess nitric acid, I'm expecting the pH, now let's just talk about expectations. I'm expecting the pH to be less than 7. I'm expecting it to be acidic because we have excess nitric acid. Okay, so now how much of that acid actually reacted? We don't know. We know initially, we can calculate the number of mole initially, okay? But what is the number of mole that actually reacted? We are here now, okay? So I would like to know what are the number of mole of nitric acid that actually reacted. What is it? Because if we have that amount, we can then get the pH of the solution, okay? But I don't know because these are my initial conditions. I don't know what happened during the reaction. So I'm going to have to go to step number 2 to find out how much of the nitric acid. I know how much, okay, I need to know the excess amount, okay, so that I can sort of figure out the amount that reacted, okay. So we're gonna start with step 2 and work ourselves back. All right, so we're gonna look at the strong acid and the strong base, okay. So yeah, let us now start calculating. All right, so in this case then, I know that the number of moles for barium is 3 times 10 to the negative 3. And remember, I have this relationship here. For 1 mole of barium hydroxide, I have 2 mole of nitric acid. So actually the number of mole for nitric acid, I'm going to say that reacted, okay, it's going to be 2 times the 3 times 10 to the negative 3. Okay, so that's just 6 times 10 to the power negative 3 mole. All right, so I know this is the amount that reacted. Now I can go back to step 1. Okay, so for step 1, I know these are the number of mole that reacted. So I can go back now to get the concentration of the acid. Okay, so the number of mole is 6 times 10 to the negative 3. And the volume that we have there is 25 cubic centimeters. So that's 25 times 10 to the negative 3. So we have 25, we have 6 times 10 to the negative 3 and we have 25 times 10 to the negative 3. So now we have 0.24, and that's the concentration, mole per cubic decimeters. Okay, now we need to now look at this acid. So if I have a monoprotic acid, the concentration of this monoprotic acid will be equal to the concentration of hydronium ions. Okay, because it's monoprotic. If it was diprotic or triprotic or any polyprotic acid, then I would have to, I would have to deal with the H's separately. So if I had an H2, I know that I would have, it wouldn't be just the concentration of hydronium. I would have to multiply by half or multiply by 2 or whatever the case is. Okay, but now we have a monoprotic acid, so things are a little bit simple for us. I know that the concentration of the nitric acid that reacted is actually equal to the concentration of hydronium ions. And why is that important? It's important because if you look at our pH formula, let's just have a look at that. It's actually equal to negative log of the concentration of hydronium. So ultimately, we need to know what the concentration of hydronium is, and that's where you relate it to it being a monoprotic acid and so forth. So the concentration then for hydronium would be 0.24 mole per cubic decimeters. So now we have negative log 0.24. Now log of 0.24, as long as it's less than 1, it's going to be a negative. So don't think you're going to end up with a negative answer. It will work out. So now we have a pH, as we predicted, less than 7 because it has to be acidic. We have a pH of 0.62. Okay, and this definitely makes sense. Okay, so that is 7.2.2. And now 7.3. This was a short question, but very heavy on the marks. So it says the percentage purity of the metal carbonate in the sample is 85%. Okay, so only 85% of it is the actual metal carbonate. The rest is just impurities. Okay, identify metal M. So remember our formula. We have percent purity. Okay, so with this percent purity, we know that this is, the actual, in this case, we've been given mass. Okay, so I'm just going to say actual mass divided by the impure sample. Okay, or let me just say the pure sample over, I want to say actual over theoretical, but in this case, we actually have the pure sample. Okay, so MCO3, the mass. Okay, let me just put it like this. So the actual mass of MCO3, and that's divided by the impure mass. Impure plus actual. Okay, of MCO3. Okay, and they've given us the percentage, so it's 85%. We don't know what this actual mass is, but we do know what this impure plus, the impure, I don't even know why I'm saying impure plus actual, it's just impure, which contains the actual. So it's actually 0.198. Yeah, so my terminology here is a bit off. So the actual, I'm just going to say now, MCO3, the mass, is actually equal to 0.198 times 85% or 0.85. Anyhow is okay. So 0.198 times 0.85, and that gives us 0.1683. Okay, So that is the mass of our metal carbonate. All right. So now what I'm going to do, I'm going to say the number of mole is equal to mass over molar mass. All right. And we now need to go look for the number of mole. Okay. I have the mass and also the molar mass. I can just write it down. Remember, we have M in itself. So I'm just going to write it like this. And then we have the carbon, and then we have 3 times the oxygen. So we don't know what this M is. We know that the molar mass of carbon is 12, and the molar mass of oxygen is 16. So 12 plus 3 times 16 plus is 60. Okay, so I have M plus 60. So over here, I have N is equal to 0,1683 all over M plus 60. Okay, but I have 2 unknowns now. I need to go sort out the number of mole. Okay, so therefore, and also in step 1, remember the relationship that we have, the ratio for initial conditions is a 2-to-1 ratio. Okay, so let's just be cognizant of that. Now when it comes to what happened, so we know that initially, initial conditions, we know that the number of mole for our nitric acid, which is the concentration times the volume, the concentration was 0,4, right? The volume was 25 times 10 to the negative 3 cubic decimeters. So we have 0,4 times 25 to the negative 3. So here we have 0,01 mole initially of nitric acid. And then we know that during the reaction, how many number of moles did we have? We are still going to figure that out. Okay, but in excess, we know that the number of mole for nitric acid is actually 6 times 10 to the negative 3. So then during the reaction, what happened? So during the reaction, we have the initial minus the excess. So we have 0,1 or 0,01 minus 6 times 10 to the negative 3. And that is what we're actually interested in. The number of moles during the reaction, not initially. Okay, so we have 0,01 minus 6 times 10 to the negative 3. So we have 0,004, or we could say 4 times 10 to the negative 3 mole. I hope you understand. So for us, in order to identify this metal, we are interested in the number of mole of nitric acid during the reaction, because initially that won't help us. In excess, that doesn't help us, because the excess nitric acid dealt with the barium hydroxide. So we need to know during the reaction. Okay, so now we have the number of mole of nitric acid, so that helps us. Okay, remember our equation, we have 0,1683. Okay. Oh, by the way, this is for nitric acid, right? 4 times 10 to the negative 3. What is the relationship that we have? We know that for 2 moles of nitric acid, we have 1 mole of the metal carbonate. So how many moles do we then have before we even calculate here? So we have a 2-to-1 ratio, okay? We have 1 mole for our metal carbonate. All right, so then it means for our metal carbonate, we're going to have half of the number of mole, okay? So half times 4 times 10 to the negative 3. So that's just going to be 2 times 10 to the negative 3 mole. All right, now we can calculate. Yeah, we can just take this and use it. All right, so our number of mole, we have 2 times 10 to the negative 3. We have 0,1683. And we have our unknown metal, the molar mass, plus 60. So the molar mass plus 60 will be equal to 0,1683 divided by 2 times 10 to the negative 3. So our molar mass, 0,1683 over 2 times 10 to the negative 3 minus the 60. And this is where you cross fingers and hope that you don't get a negative answer. Okay, so 0,1683 divided by 2 times 10 to the negative 3 minus 60. So you have 24,15 grams per mole. So what is that metal? We're going to go to our periodic table and look for that metal. We're looking at group 2, remember? So 24, magnesium. Okay, so we see that magnesium is metal, is the metal. So M is magnesium. I don't know, were they trying to give us a tip? It is M, it starts with M, so magnesium. I don't know, could be. So yes, magnesium 24,15. Therefore, we actually have magnesium carbonate. Okay, and I think that is it for question 7. All right, for 8 marks. Second last question. Question 8, forming part of the electrochemistry. Okay, so it says a cleaned pure copper strip is placed in a beaker containing a colorless silver nitrate solution at 25 degrees as shown below. So that tells us that we're dealing with standard conditions, right? Temperature, concentration. All right, so yeah, so after a while it is observed that the solution in the beaker becomes blue. Okay, why would it become blue? Well, the copper is busy dissolving. Okay, so as it dissolves and as it forms a reaction with the silver nitrate, then you get the blue color. Now 8.1.1, it says, write down one other observable change besides the solution turning blue. Okay, because the copper is dissolving, we can say that the copper strip loses mass. I almost said weight. I don't know, maybe it's because it's January and we're trying to lose the weight we gained in December. But yeah, the copper strip loses mass. Okay, it's only what, 1 mark. Yeah, that's because in this case we can say with confidence that the copper will oxidize. Okay, it dissolves, loses mass. It's fine, 1 mark. 8.1.2, it says write down the name or formula of the oxidizing agent. Okay, so what do we have? We have silver, we have the nitrate, and we have our copper. Okay, which now in solution. All right, so we know that as it loses mass, it's oxidized, right? And then the oxidizing agent between the two, in this case, I would select silver. Okay, the nitrate is in solution. Yeah, the silver could probably form a precipitate, but actually I'm not sure about that, so don't take my word for it. But if I had to choose between silver and nitrate, I would say that silver would be the oxidizing agent. Okay. Oh, they want the formula. Oh, the name or formula. Okay, so it's cool. Now 8.2, it says explain the answer to 8.1.1 by referring to the relative strengths of the oxidizing agents or reducing agents. Okay, so I'm going to look again at copper, at silver, at the nitrate. Let's just go to table B, 4B. I know you guys are comfortable with 4B. Not so much 4A. For me, it doesn't really matter, but let's just stick to what you guys are comfortable with. All right, so we see, I hope you see, that there is silver, and then we have copper, 2 plus. Then with the nitrate, you have two options. Hey, you either have this nitrate over here, that nitrate over there. I would tend to go with this one. Okay, not nitrogen monoxide. All right. Hence, it actually supports, which one is the, what is the question again? The formula for the oxidizing agent, I would go with silver instead of the nitrate. Okay, so let's not consider this nitrate over here. All right, so what I see then with the copper, I can see that the EMF there is positive 0.34. All right, the silver, we don't really need to write this down, positive 0.8 volts. Same with the nitrate. Okay, but yeah, the way in which I wrote this, I should have actually written the nitrate above. All right, so basically copper is the strongest reducing agent, okay, because if you look at your heading here, it says increasing strength of reducing agent. So obviously your copper will be the strongest reducing agent. Okay, it will be oxidized. Okay, and then silver on the other hand will be your strongest oxidizing agent. Okay, as it will be reduced. Okay, let's just put it there. Yes, it will be the strongest oxidizing agent as it will be reduced. Okay, so what it does, it easily receives electrons, all right, that are coming from copper, because remember copper as it is being oxidized, it lets go, it loses electrons. Okay, so silver will easily receive electrons from copper. Okay, and therefore it reduces. Okay, so yeah, let's just go back to the question. All right, so yeah, it says explain the answer to question 8.1.1 by referring to the relative strengths of the oxidizing agent. So we did. We showed there the strengths, okay? And we know that table 4b, as you go up, it increases in reducing agents. So we know copper is the strongest reducing agent, silver is the strongest oxidizing agent. The copper, we're expecting it to be oxidized, the silver to be reduced. Why? Because it easily receives electrons from copper. Okay, I don't know what else to include, but we can tell that story. True story. Okay, so now 8.3. So a galvanic cell is now set up using copper and silver strips as electrodes. Okay, a simplified diagram of the cell is shown below. All right, so we can see, just make that a little bit bigger. So silver there, we've already talked about copper, we've already talked about silver. Silver will get reduced, copper will get oxidized. Okay, so as a result, you can then say this is the cathode, right? Because reduction has occurred there. Let me just make this a little bit, yeah. So basically, this is the part where it gets reduced. Okay, so therefore it's the cathode. Okay, red cat. And this side, that is your anode. Okay, where oxidation occurs. All right, so this is where your copper is that will get oxidized, and you have your electrons flowing in this manner. And yeah. So now 8.3.1, it says write down the name or formula of electrode A. Okay, so electrode A, that's simply the silver. Okay, you can write the name. And then 8.3.2, it says the name or formula of solution B. Okay, so solution B, remember we have copper there. So as copper oxidizes, you will be left with the copper in solution. Okay, copper ions, cations. Okay, so and in the solution we have sodium. No, why am I saying sodium? Sorry. Yes. So now in the solution, there's some nitrates. Okay, so the copper and the nitrate will come together, and the name or formula of solution B, you'll have copper nitrate. Remember, copper has 2 plus, your nitrate is 1 minus, so we're just going to need 2 of those. Okay, so that is your copper nitrate solution. And then this is the answer, by the way. 8.3.3, it says the overall balanced equation for the cell reaction. So what happens at the cathode, what happens at the anode, and then what is our final answer? So at the cathode, we did say it's silver. Okay, so we have the silver ions with the electron, and you get the solid. Okay, and then at the anode we have copper. Okay, so you had your copper solid initially, and then it oxidizes, becomes copper 2 plus, and then you have 2 electrons. Okay, so we can see that the electrons are not balanced, so therefore we're going to need to multiply here by 2, multiply here by 1, and so when we write our net balanced equation, so we're going to multiply this by 2. Just use a different colored pen. So we're going to multiply everything by 2 over here. Okay, so at the end we have 2 silver ions, and then we have the copper, and then here we have 2 silver, and then we have the copper ion. Okay, so yeah, we can just extend that a bit. So that the copper is not left out in the cold. But yeah, basically that is your overall balanced equation for the cell reaction. And then 8.4. Alright, so it says the salt bridge contains potassium nitrate. Okay, remember potassium, positive, nitrate, negative ion, an ion and a cation. So write down the formula of the ion in the salt bridge that will move into the silver ion solution. Okay, so we need to choose and then motivate. Alright, so we know that in the, let's start with the anode. Okay, although they're asking about the cathode. Okay, so with the anode, you have your copper, right? And with copper, as it releases electrons, and the electrons are coming to the other side, so electrons are busy going that way. This solution in here is becoming positive, because now you're starting to be left with copper 2 plus. So what will attract to the copper 2 plus ions it is your nitrate. Okay, because opposites attract, right? And then here you have electrons that are busy going to your cathode section. Okay, so what happens then? Your solution in here is starting to become negative. Okay, even though your electrode here of silver is busy forming, you still have electrons that are still coming in. Okay, and what will attract to the negative charge in the cathode beaker? It will be your potassium. So to answer the question, it will be the potassium ions, so K plus. And give a reason for your answer. It's 2 marks. It goes back to opposites attract. I don't know if that's a simple answer to give, but you need to explain that copper, when it loses electrons, it becomes positively charged. You are left with cations. Therefore, the negative part of the salt bridge solution will be attracted to that copper, which is the nitrate. And then on the other end, the electrons are moving into your cathode beaker. So it will become more negatively charged, and as a result, the potassium will be more attracted to the negatively charged ions in there. And yeah, that's it. And I think we are done with question 8. We've come to the end of the paper. Question 9. You must be relieved. I must say, chemistry was a bit more challenging than physics. I have to think quite a lot. A lot of mistakes could have easily been made in this paper. So I now understand my students when they said, yeah, I thought I was going to get a distinction for physical sciences until chemistry happened. So easy. But for the matrics for this year, use this paper as practice so that you are aware of how they can ask questions. I mean, especially with the organic chemistry section, I'm used to question 1, the first 4 questions being organic, but they just cut it to the first 3. So yeah, just be prepared either way. So question 9, an electrolytic cell is set up to purify a piece of copper that contains silver and zinc as impurities. All right. A simplified diagram of the cell is shown below. Electrode R is impure copper. Okay, so that is a nice tip. If this is impure copper, that tells you that this is the anode. All right, basically where oxidation occurs, the loss of electrons. Okay, so electrons are moving in that direction. Therefore, this side here would be the cathode where reduction occurs. Okay, so that's the cathode. Yeah. So this is going to end up losing a bit of mass. The impurities, as the impurities go down, this loses mass. And over here you have pure copper forming around, which is what you want. Okay, because you're purifying. All right, so now 9.1 theory question. It says define the term electrolysis. Okay, they're not asking the chemical change that happens in an electrochemical cell. They're just asking what is electrolysis. So electrolysis basically is a process where electrical energy is used to produce a chemical change or a chemical reaction. Okay, so that's just that definition. 9.2, write down the reaction taking place at electrode Q. Okay, so this is what, 2 marks. So at Q, we know that reduction is occurring. And with reduction, like when you look at your table of standard reduction potentials, it's written standard reduction potential table. So the way the formula is written there, that's how you write it. So for copper, you will then have copper 2 plus. I don't know if it's necessary to put this in, but yeah, just to be safe. And then you have 2 electrons there. And then now you have the copper solid. Okay, so the way it's written, in that table, 4B or 4A, that's how you write it for the cathode. But whenever you are dealing with the anode, like on this end, this side, the anode, you swap things around. So you start with your solid and then you end up with your ions and electrons. Okay, that's what happens at the anode. Okay, so that's 9.2. And then 9.3, in which direction do the electrons flow in the external circuit? Choose from Q to R or R to Q, so we can see the electrons are flowing from R to Q. And then it says, calculate the current needed to form 16 grams of copper when the cell operates for 5 hours. Okay. Okay. So for 5 marks, calculate the current needed to form 16 grams of copper when the cell operates for 5 hours. Okay, so we're going to refer back to this equation over here. We've been given the mass of copper. So I'm thinking we need to get the number of moles for copper. Okay, so that's basically the mass over the molar mass. Let's just check quickly what the molar mass is for copper. I hope you can see there, it's 63,5. Okay, so our mass is 16 grams and our molar mass is 63,5 grams per mole. So basically the number of moles that we have there is 16 divided by 63,5. Yeah, that's 0, yeah, I think I like fractions better because I don't want to lose, I don't want to dilute this answer going forward because I think we still have a long way to go. So that's 32 over 127. All right, and then looking at our equation, like I said, we're going to have to refer back to it. We can see that the number of moles for copper in relation to the number of moles for the electrons, we have a 1 to 2 ratio. Okay, so therefore the number of moles for the electron will be twice that of copper. And why is that important? Okay, we're going to look at our formula sheet. All right, so basically we're going to use this formula where it says the number of moles is equal to N over Na. So Na is Avogadro's constant, okay? And N, in this case, well, it's the number of molecules, number of atoms, per mole. So basically, yeah, actually, number of molecules, number of atoms. So in this case, I want to get sort of like the number of electrons here, okay? But just follow with me. Let's just follow and then see what we're going to do with that. So we have Avogadro's number. We also have the number of mole. So now let's see here if we can get this number. So it's going to be number of electrons. Sorry, mole. Not the number of electrons. This N is the number of moles for the electrons. And then we have Avogadro's number. So we have 2 times 32. That's actually 64. 2 times 32. And then we have Avogadro's number, which is 6,02 times 10 to the power 23 per mole. Okay, so this is mole, and this is per mole. So we're going to get a number here. So if we're going to take this number, multiply it by 2, okay, then multiply it by 6,02 times 10 to the 23. All right, so we're going to get 3,033,7 times 10 to the power 20. All right, and then what are we going to do? So from here, we're going to use another equation where we get, there's the number of electrons that we actually get. Okay. Then we're going to use this number and we're going to take charge over the charge of an electron. Why am I doing all of this? The question asked for the current passing through, okay? Now if you look at the equation, we have current being equal to charge over delta T. So we're basically looking for charge over here. Sorry, I should have started with this equation so that we know what we're working towards. All of this that we're doing, we're trying to get the charge because we've already been given the time, okay, which was 5 hours, I think, but we'll get back to it. Yeah. So charge then will be equal to the number of electrons times the charge of an electron. So we have 3033,7 times 10 to the 20. Multiply the charge of an electron, I hope you see, it's 1,6 times 10 to the negative 19. Okay, let's go back up again. Okay, remember, calculate the current needed to form 16 grams of copper when the cell operates for 5 hours. Okay, so anyway, the charge that we are eventually getting, so it will be that number multiplied by the charge of an electron, 1,6 times 10 to the negative 19. And we get an answer of 48,539,21 Coulomb. Alright, now let's talk about this time. 5 hours, we need to convert it to seconds. Okay, let me just get that time. So 5 hours, I know that there are 60 minutes in an hour and there are 60 seconds in a minute. So we have 5 times 60 times 60, and that is 18,000. So now finally, current is equal to charge over time. So our charge is 48,539,21, and that's divided by 18,000. So yeah, there's my answer there. Let me see, can I go back there? No, I can't. So 48,539,21 divided by 18,000. And that gives us 2,696, so that's basically 2,70, if we round it off to 2 decimal places, amperes. Okay, that is the current that is passing through, or the current needed to form the 16 grams of copper. Remember, this is an electrolytic cell, so you do need current passing through, electrical energy. And then the last question. So it says, during this electrolysis, only copper and zinc are oxidized. Okay, remember we had the impurities, they did say. So a piece of copper contains silver and zinc as impurities. So what do we have? We have copper, we have zinc, we have silver. Okay, and they tell us, they say give a reason why, only copper and zinc are oxidized. So copper and zinc, they are oxidized. Give a reason why the silver is not oxidized. Okay, we have been discussing, well, from question 8, but let's just go back to the table, table 4b. Okay, and let's have a look here. Where is zinc? Should be somewhere up there. Okay, I see it. Let's see. All right, so let me just remove this nitrate. We're not looking at it anymore. So there we have silver, we have copper, now there is zinc. Okay, so I'm just going to put it there. Zinc is way up there, and it has negative 0.76 volts. Then we come to copper, which has 0.34 volts. And then we get to silver, which is 0.8 volts. So what does that tell you? Silver, yet again, is the strongest oxidizing agent. Okay, meaning that it is reduced. Then you have zinc being up there. So this one is the strongest reducing agent. Okay, therefore it is being oxidized. Okay, so let's go back to our question and finalize it. So now they're saying during the electrolysis only copper and zinc are oxidized. Yes, we can believe that. So this is also oxidized. Now it says give a reason why the silver is not oxidized. Silver is not oxidized because it is the strongest oxidizing agent. Therefore, in this case, it is being reduced. Okay, so because it's being reduced, it has no time to be oxidized. It wants those electrons. Okay, so it accepts, it easily receives or accepts. Okay, I'm going to say receives. Okay, the electrons that are coming from that impure copper sample. Okay, so it easily receives electrons. It wants to be reduced. It doesn't want to give away electrons. It wants to take them. All right, so I would give those two reasons. So it is the strongest oxidizing agent, therefore it will be reduced, and it easily receives electrons. Okay, whereas the zinc and the copper, they are more likely to be oxidized. All right, and this is it. We're done with this paper. All right, I hope you have learned a thing or two. Any comments, any suggestions, any input, please do comment below. Do not forget to like our videos and also subscribe to our channel, and also tell your fellow matric classmates about this channel. And yeah, tell us ways of improving. Do give a comment here and there if we're doing a good job. We're here to serve you, so please tell us how we can best serve you. And that's it from me.